Hello everyone, thanks for participating in this online workshop from different time zones. My name is Tarane and I'm a PhD student at the University of Pittsburgh. The work that I'm presenting now is a funded project from Florida Department of Transportation that I completed during my master's at Florida Atlantic University with a great collaboration with the Florida International University. Here is a glance of today's presentation. I will start with a small background about transit signal priority and freight signal priority. Then I will continue with the objectives of this research, the methodology, and I will continue with the results, the developed guidelines, and some validation and evaluation that we completed. Then, last but not least, I will conclude the presentation with some conclusions and recommendations for future works.
We are wasting a lot of time and money every day in heavy traffic, especially in urban areas. To give you some numbers, trucks are wasting almost $28 billion annually just behind the signals, and buses are usually wasting 20% of their trip time. I'm not happy to say that, but let's be honest. By the year 2045, the number of trucks will grow by 30%, and the number of vehicles will grow by almost 20%. At the end of the day, all these vehicles will result in more congestion. Now I want you to close your eyes. Imagine the situation of getting stuck behind a heavy, giant truck at the signalized intersection. The signal turns green, the truck passes, the signal turns red, and you're still there forever. That's because of the lower acceleration and deceleration of the heavy vehicles. Don't worry, open your eyes. Traffic engineers are here for you. Nowadays, everything is intelligent. We are proposing the use of intelligent transportation system techniques such as TSP and FSP to tackle these miserable situations. So what are TSP and FSP? Transit and freight signal priorities are some techniques that detect the approaching buses and trucks, inform the traffic signal, and request for more green time. In that case, there is no need for them to stop and start moving again at the signalized intersection. Therefore, not only the number of stops, travel time, and delay will decrease, but also fuel consumption, CO2 emissions, and pavement maintenance costs will decrease. Although the implementation of TSP and FSP on our case study in Sunrise Boulevard, Broward County here in Florida performs really promising, but that was not the only outcome. Yes, we saved around 30% of travel time for buses, 22% for trucks, and almost 16% of travel time for passenger cars on 20 signalized intersections in Sunrise Boulevard. But this is not the end of the story. Here's the challenge. Are all intersections eligible for the application of TSP and FSP? Is it feasible to implement them at all conditions? Well, it depends. So in this research, we also developed some guidelines for traffic agencies to determine if it's applicable to implement them or not. These guidelines are developed based on several criteria and factors and after running hundreds of scenarios. I am thrilled to mention that by the use of these guidelines, hopefully we won't suffer from being stuck behind a huge truck anymore. To that day and all its benefits. We planned regionally, acted locally, and fantastically, it's applicable globally. Thank you.
Now you have some ideas what we did in this project. Without further ado, I'd like to mention that, as we all know, the demand for the movements of goods are increasing all around the world. Even during the COVID-19 pandemic, the impacts on freight movement in the U.S. was the smallest hit among other forms of ground transportation. As you can see in these following figures, the number of trucks and buses are increasing steadily. There is an expectation for a great increase from 60% to 78% in road transportation until the year 2045. All the predictions and expectations are showing that with a growing population, especially in urban areas, the roads will be more congested and there is a need for coming up with new solutions. Traffic congestion in cities will result in more queue, more number of stops, more travel time, and more delays. Consequently, it will bring less mobility, less safety, less reliability, and less efficiency. The traffic signals were historically a solution for urban congested intersections. However, the disruption caused by signals affect its efficiency. Intelligent transportation systems with some techniques such as transit signal priority and freight signal priority will become helpful at some conditions that we will talk later. On multimodal corridors, trucks are deteriorating the systems by their slow dynamics and slower acceleration and deceleration. Only one stop of a truck could have significant impact on the mobility of all vehicles. Therefore, it is of great importance if we can do something to reduce the number of stops for trucks. Now let's move to the similarities and differences between transit signal priority and freight signal priority. Both technologies follow the same procedure. They detect the approaching vehicle, alter the signals, and the traffic signal provides early green or green extension to them. The technologies could reduce the wasted time and fuel, and as a result of that, not only the last mile delivery will be smoother and more reliable, but also the reduction in braking will decrease the pavement wear. Here are some of the documents, reports, and papers that we referred during our literature review. I don't want to go in detail, but what we found from the literature was the lack of any combination of transit signal priority and freight signal priority at the same time. Overall, we got to this point that TSV and or FSV might not be effective for all conditions, and as I mentioned before, there were some guidelines available for implementation of either TSV or FSV, and in general, there were a lack of studies for the implementation of freight signal priority. Therefore, we came up with the idea of simultaneous implementation of TSV and FSV, and for that, traffic agencies need some guidelines. So the objectives of this research are first to develop some guidelines for the identification of feasible corridors, and then to evaluate the effectiveness of TSV and FSV. The research methodology is as follows. First, after a couple of meetings with the stakeholders, we decided about the location of the case study. Then we did the data collection in terms of freight operation and transit operation. After developing the base model in Basin, we calibrated the model with Bluetooth travel time. Then we developed various scenarios and we ran them and evaluated the results. By the analysis of results and the gap between literature, we considered different factors for the development of guidelines. Afterward, by providing the FSB and TSB checklist according to the literature and considering a random single intersection, we developed the decision trees. Then, we validated the guideline by taking into consideration various scenarios and evaluating the results based on the travel time and delay. Starting with the case study, it was located in Sunrise Boulevard, Broward County in Florida. This boulevard is located near a seaport and an airport. Therefore, it has high volume of trucks, and also it has 5 bus routes, 4 buses per hour per direction. We applied our methodology on 20 signalized intersections in a 4.2 miles corridor in Sunrise Boulevard. In terms of data, we chose morning peak hour for data collection. We collected traffic counts, truck characteristics, and transit data. We modified the model in Basin 11, and then we calibrated the model based on travel time gathered from Bluetooth data. We applied the check-in and check-out detectors as is shown in the figure, and in the next slide you can see the developed model in Basin. After several meetings with the stakeholders, 7 scenarios were selected for evaluating the performance of TSP and FSP on Sunrise Boulevard, including only freight signal priority, conditional FSP type 1 by excluding type 5 of trucks, which we didn't want to give priority due to the highest amount of them, and less important because they are not actually, mostly not the heavy vehicles. Then it was conditional FSP type 2, which is excluding trucks type 5, 6, and 7, basically providing priority only to the combination trucks. Other scenarios are only transit signal priority, both FSP and TSP, and other configurations of conditional FSP with TSP. We run the simulations for 5 times, each of them 1 hour and 15 minutes, with 15 minutes warm-up and 1 hour simulation. After evaluating the results from various scenarios and comparing them with the no priority scenario, the consideration of only freight vehicles or transit vehicles shows that the TSP and FSP scenario was performing better. Also, in the comparison of all vehicles, the results confirm that the simultaneous implementation of TSP and FSP is providing the lowest travel time. Based on the literature, we discovered some of the important factors for considering in the guidelines, such as volume overcapacity, slack time, bus occupancy, bus frequency, trucks weight, and so on. In order to compare the values and importance of different vehicles, there should be a scale. We referred to Hodges' study 2019, and we used the mathematical model below to allocate different dollar values to the factors. We consider travel time to access the values. C is the total cost of delay for a specific signal configuration. D is the delay. Beta and O are values of travel time and occupancy based on the table that you can see. And then to make the decision, B can be calculated by subtracting the total cost of no priority model from the specific signal configuration. We selected one single intersection randomly in order to run various configurations for developing the guidelines. As you can see, we considered different overseas, different freight percentage, and different transit frequency on both major road and minor road. Afterward, based on the results from the literature, we created our own checklist to evaluate the feasibility of TSP and FSP application on a specific corridor. Here in this slide, you can see the final guidelines and decision trees based on different conditions, such as the major road or the minor road, by applying TSP only, FSP only, or both of them, and which are our recommendations based on the situation of the corridor. As you can see on top of the figure, there is a need for at least 5 seconds of slack time that a corridor could be feasible for the application of FSP and TSP. In order to validate the guidelines, we applied the guidelines on our case study. So for that, we checked the slack time on all of the intersections separately to see if they have at least 5 seconds of slack time, and all the intersections fulfilled this requirement. Afterward, we decided to determine the application of the FSP and TSP priority on only the major road, and to continue on validating the guidelines, we checked the applicability of FSP and TSP based on the checklist that we developed before on each of the intersections. Since all the intersections in our case study fulfill the requirements for the application of FSP and TSP, we decided to develop different simulations to compare with the no priority scenario. As you can see, we developed the TSP only, FSP only, and the combination of both priorities in addition to the base model that we had in order to make the real comparison. The results from travel time cost are provided here and indicating that FSP only has the highest profit with 6.63%, and the second place goes to the application of both FSP and TSP with almost 6%. Therefore, it is more reasonable to provide priority to two modes of transportation rather than only one, with almost the same benefit for the system. For evaluating the results, we collected the average travel time for all intersections after 5 runs. As you can see in this table, for the eastbound major road, the application of both TSP and FSP saves the most travel time in comparison with other scenarios. Obviously, in the FSP only scenario, trucks saved the most travel time, and in the TSP only scenario, buses saved the most. Same trends happened in the westbound results in the next slide, and you can see that FSP and TSP performs better than other scenarios. The average delay on the major road, as it was expected, was lower in the TSP and FSP scenario, which is shown by yellow in this chart. The highest delay belongs to the no priority scenario with the dark blue. In terms of the minor roads, as we didn't provide any priority on them, the side streets face higher travel time in the priority scenarios, either TSP or FSP or both. The highest travel time happened in the scenario with the simultaneous application of FSP and TSP. TSP scenarios sometimes had the lowest travel time and delays because they provided priority to the lower volume than the trucks and passenger vehicles in other scenarios. The minor road delay box plot illustrates that the base model has less variation in delays, and FSP and TSP model, the yellow box, has a greater variation in terms of delays. The median in each box plot shows the vehicles that each of the scenarios serves. To conclude, here are some points that I'd like to mention. The application of both TSP and FSP has positive impacts on the movements of freight and transit vehicles. The highest mobility resulted by the application of both TSP and FSP. To consider a corridor eligible for signal priority, the first factor is to have at least 5 seconds of slack time. By applying the priority on only the major road, the minor road will face more delays, so it's more beneficial to deploy the priority on both directions if it's possible. The developed guidelines in this study can be used in any types of streets, major and minor or both, and for different priorities. It is recommended to use these guidelines in corridors with high volumes of freight movements. And finally, this study indicates that the application of TSP and or FSP might not be helpful in all the conditions. Some suggestions for continuing this research could be the identification of different aspects of freight movement, developing scenarios with different priority weights on TSP and FSP, providing priority based on the freight commodities if applicable, applying FSP and TSP on a wider network and considering the use of these developed guidelines, and finally, the deployment of FSP and TSP strategies on certain corridors could be helpful. Thank you so much for your attention, and I'd like to take any question or suggestions if you have any. Thank you.